In the mid-20th century, the prevailing scientific model for Venus described a wet, tropical planet. The cloud cover was so dense that astronomers assumed the surface was shielded from the sun. They imagined humid swamps beneath those clouds, possibly life. This assumption was so embedded in mission planning that early Soviet probes carried sensors specifically calibrated to detect water. The reality was the exact opposite. The atmosphere wasn't a shield, it was a lid. It trapped heat and created a runaway greenhouse effect. With surface temperatures around 475 degrees Celsius, the first few probes didn't just fail, they were physically obliterated by immense atmospheric pressure before they could transmit a single image from the surface. This created a new consensus. Even if a lander could survive the descent, photography would be useless. The atmosphere was 90 times denser than Earth's. Scientists predicted that little to no sunlight could penetrate that depth. The surface of Venus, they concluded, was locked in perpetual absolute darkness. The Soviet engineers ignored this model. They equipped the Venera 9 lander with a floodlight just in case, but they also programmed the camera to scan immediately upon landing. Darkness or not, the footage that returned proved the darkness theory completely wrong. But it was the later missions, specifically the panoramas from Venera 13, that sent back data no one can fully explain even today. The Soviet engineers were working with catastrophically bad data. In 1967, the accepted model suggested the surface pressure of Venus was roughly 20 times that of Earth. This was high, but manageable with reinforced aluminum. The Venera 4 probe was built to these specifications. It entered the atmosphere and deployed its parachute. Expecting a slow drift down to the surface, it never made it. The probe stopped transmitting at an altitude of about 27 kilometers. It didn't burn up. It was physically crushed by pressure that far exceeded its structural limits. The atmosphere at that altitude was already surpassing the probe's designed capacity, and it was nowhere near the ground. This failure revealed the scale of the problem. The pressure wasn't 20 times that of Earth. It was closer to 90. At the surface, that's the equivalent of being 1 kilometer underwater on Earth. The team had a limited window before the next launch opportunity in 1969. They couldn't redesign the entire pressure vessel in time, so they tried to bypass the problem through descent speed. For Venera 5 and Venera 6, they reduced the size of the parachute. The logic was simple. If the probe fell faster, it would spend less time in the crushing upper atmosphere. Hopefully, it would reach the surface before the heat and pressure destroyed it. The plan failed. Both probes imploded roughly 11 kilometers above the surface. This forced a total redesign for Venera 7. The engineers abandoned the idea of a standard aerospace vehicle. They effectively began building a submarine. The new design featured a forged titanium sphere capable of withstanding 180 atmospheres, double the expected load. They removed almost all scientific instruments to save weight for armor. The windows were removed. The solar panels were replaced with a heavy internal battery. Venera 7 launched in August 1970. Upon arrival, the parachute reefing cords melted during descent, causing the parachute to fail during the final stage. The probe didn't float down. It fell. It impacted the surface at roughly 17 meters per second on mission control. The telemetry stream flatlined immediately. The mission was marked as another failure. It was only during a post-mission review of the raw radio tapes that an astronomer noticed a pattern in the static. The probe had not died. It had toppled over on its side, pointing its antenna away from Earth. But it was still whispering. By processing the noise, they recovered 23 minutes of temperature data from the surface. It was the first time a human machine had transmitted data from the surface of another planet. The data confirmed the surface was roughly 475 degrees Celsius. It proved a machine could survive, but it also proved that any cameras sent to this world would need to be built like a tank. That the survival of Venera 7 proved that a titanium sphere could resist the crushing pressure of 90 atmospheres. The problem for the next generation of probes was the temperature. The surface of Venus sits at 475 degrees Celsius. This is hot enough to melt lead, zinc, and tin. It's also hot enough to destroy standard silicon electronics instantly. The engineers couldn't simply insulate the lander. Insulation only slows down heat transfer. Eventually, the heat gets in. They also couldn't use active cooling systems like fans or radiators. A radiator works by dumping heat into cooler air. On Venus, the The air outside is hundreds of degrees hotter than the machinery inside. The solution was to turn the lander into a temporary heat sink. Before the lander separated from the orbiter, the system circulated supercooled fluid through the pressure vessel. This brought the internal temperature of the probe down to -10 degrees Celsius. This gave the probe a thermal head start. It essentially began its mission as a block of ice falling into a furnace to handle the heat generated during descent. The engineers used a phase change material. They packed the interior with lithium nitrate trihydrate. This chemical has a melting point of 30 degrees Celsius. When a substance melts, it absorbs a massive amount of energy without rising in temperature. As the heat from the Venusian atmosphere penetrated the titanium shell, it went into melting the lithium nitrate rather than frying the electronics. This bought the lander roughly 50 to 60 minutes of operational time before the system boiled over and failed. The camera itself required a completely different approach from standard photography. A television camera from the 1970s used a cathode ray tube. These tubes were large, fragile, and required glass lenses that would crack under the external pressure. The engineers couldn't risk putting a large glass window in the side of the pressure vessel. A structural failure there would cause an immediate implosion. Instead of a camera, they built This is a mechanical scanner rather than a lens-based imaging system. The device remained safely inside the cooled titanium sphere. It looked out through a tiny cylindrical quartz window that was thick enough to withstand pressure. The mechanism was simple and robust. A small mirror rotated back and forth behind the window. It collected light from a single point on the surface and directed it into a sensor. The sensor measured the brightness of that single dot. Then the mirror moved slightly to measure the next dot. The probe transmitted this data as a stream of numbers. It didn't send a video signal. It sent a long string of telemetry that earthbound computers reconstructed line by line. This method was slow. It took many minutes to build a complete panoramic image. If the probe overheated before the scan was finished, the image would cut off. The engineers were trading speed for durability. They were betting that a slow mechanical I had a better chance of surviving the conditions than a complex electronic one. But this only matters once you see what happened when that eye finally opened. On October 22, 1975, Venera 9 survived the descent and transmitted data for approximately 50 minutes. It landed on a steep slope of roughly 20 degrees. The engineers had prepared for the worst-case scenario regarding visibility. They assumed the thick clouds would block all sunlight, plunging the surface into deep twilight or total darkness. To counter this, the lander carried powerful halogen floodlights to illuminate the ground in front of the camera. When the lens cover popped off, the sensors detected immediate illumination. The floodlights were unnecessary. The surface of Venus was not dark. The ambient light levels were comparable to a cloudy summer day in Moscow. The thick atmosphere scattered the sunlight evenly, creating a soft, diffuse glow that eliminated harsh contrasts but provided plenty of light for the telephotometer. The camera began its scan. It took 30 minutes to build the full panorama. As the data arrived on Earth, the scientists saw something that contradicted years of theory. They expected to see a sandy desert or a landscape worn smooth by erosion. The atmosphere was dense, so they assumed strong winds would scour the rocks down to pebbles. The image from Venera 9 showed the opposite. The ground was covered in sharp, angular rocks. The edges were jagged and broken. This implied that the surface was geologically young. It also proved that the wind speed at the surface was negligible. The rocks had not been eroded by wind or sand. The atmosphere was calm. The image also revealed the clarity of the air. There was no fog or dust near the ground. The horizon was clearly visible in the corners of the panoramic frame. 3 days later, Venera 10 landed over 2,000 kilometers away and operated for 65 minutes. It touched down on a much older, smoother plane. Its images showed flat slabs of rock resembling dried magma flows. The difference between the two landing sites proved that Venus was not a uniform wasteland. It had distinct geological regions. It had mountains, slopes, and plains. The primary discovery, however, remained the light. The fact that the sun could penetrate 90 atmospheres of carbon dioxide showed that significant diffused sunlight reached the surface, contradicting earlier predictions of total darkness. These two black and white images were the first direct look at the surface of another planet, but they were limited by their lack of color. The scientists could see the shapes, but they couldn't see the true nature of the chemical world they had touched. And this is where the story starts to get uncomfortable.